Here is a combined summary of the 2 pages. The recent report of room temperature superconductivity in nitrogen-doped lutetium hydride, LUN, by Dasenbrock-Gammon et al., has sparked controversy due to the lack of reproducibility by other researchers. This study aims to investigate the origin of the near-room temperature sudden change of electrical resistance in LUN samples. Using a well-controlled experiment protocol, the authors repeatedly reproduce the near-room temperature resistance change in LUN samples and compare its behavior with the initial pure Lu in a normal metallic state. The results suggest that the sharp resistance change is attributed to a metal-to-poor-conductor transition rather than superconductivity. The experiment involves loading a piece of pure Lu foil with an H2N2 gas mixture and conducting in situ van der Paa-4 probe resistance measurement in a diamond anvil cell, DAC, under different pressures and temperatures. The temperature-dependent resistance of the sample, including the initial pure Lu metal and the later reacted LUN, is obtained without extra sample change, manipulation, or exposure to air. The initial resistance temperature curve of the pure Lu metal shows a positive temperature coefficient of resistance and residual resistance below approximately 15 K, featuring a typical normal metallic state. After reaction with the H2N2 gas mixture, the temperature-dependent resistance curve of the reacted sample becomes quite different, with a sharp upsurge of resistance emerging at approximately 250 K during warming. However, the entire resistance curve, above and below the sharp change, is higher than that of the initial pure Lu metal, indicating that the sample forms a worse metal above 250 K. The experiment has been repeated and reproduced without failure, and the sharp resistance change has also been observed at releasing pressure to 5 and 2 gigapascals. The temperature dependence of resistance of the reacted sample below approximately 230 K is linear and basically parallel to that of the initial Lu metal. The absence of zero electrical resistance, a hallmark of superconductivity, contradicts the superconducting claim. Here is the combined summary. The LUN system has sparked intense research due to claims of near-room temperature superconductivity. However, the lack of reproducibility and inconsistencies in previous studies have raised concerns. The authors of Ref. 1 reported a sudden resistance change in the LUN sample, which was linked to a blue to pink color change. Despite numerous attempts, other groups failed to replicate this finding. The present work reveals that the sample microphotographs in Ref. 1 do not provide clear details of the sample preparation and measurement setup, casting doubt on the results. In contrast, the authors of this study conducted in situ resistance measurements of pure Lu foil during its reaction with H2N2 gas mixture at broader pressure and temperature space. The results show that the abrupt resistance transition near room temperature can be reproduced in the dark blue LUN sample, but not at the experimental conditions provided in Ref. 1. The increase in sample resistance after reaction compared to the initial pure Lu metal rules out attributing the observed sudden resistance change to any superconducting transition. The LUN sample was prepared by reacting pure Lu foil with H2N2 gas mixture at a certain temperature and pressure. The sample synthesis and characterization were performed using a customized beryllium-copper alloy diamond anvil cell, DAC, with a non-magnetic rhenium gasket. The diamond anvil culet size was approximately 300 micrometers. Cubic boron nitride with epoxy resin was used as an insulating material for electrical measurements. 4 platinum electrodes were arranged symmetrically on the Lu sample to monitor the resistance variation during the chemical reaction. The results indicate that the blue to pink color change is not a critical feature associated with the sudden resistance change, and the lack of reproducibility in previous studies can be attributed to the random multiple metal insulator phase mixture. The controlled baseline of the initial pure Lu resistance is essential for consideration of superconductivity. This study provides concrete and reproducible results, which can guide the scientific community towards addressing many questions raised on the LUN system, other than the ostensible near room temperature, room pressure superconductivity. Here is a combined summary of pages 5 and 6. Figure 1 presents in situ electric resistance measurements of a lutetium, Lu, foil sample loaded with a hydrogen-nitrogen gas mixture in a diamond anvil cell, DAC, at 10 gigapascals and 295 K. The optical microphotographs of the Lu foil sample before and after a 5-day reaction show a distinct change in the sample's surface from metallic luster to dark blue, accompanied by a decrease in light reflection due to the reaction. The sample size increases slightly after the reaction, and the sample chamber shrinks, indicating consumption of the gas mixture. The temperature-dependent raw resistance values during warming from 2K to 300 K are shown for the initial pure Lu metal before reaction and the same sample after reaction for 5 days at 10 gigapascals and 295 K. The blue and red curves demonstrate a significant change in the resistance behavior of the Lu sample after reaction. The references cited on page 6 discuss recent studies on near-ambient superconductivity in lutetium hydrides, including evidence for and against superconductivity in these systems. The references cover a range of topics, including the effect of nitrogen doping and pressure on the stability of cubic Lu3, the pressure-induced color change in Lu2, and the electronic and magnetic properties of Lu and Lu2. Notably, some studies report evidence of near-ambient superconductivity in nedoped lutetium hydrides, while others find no evidence of superconductivity. The cited references also explore the percolation-induced resistivity drop in cold-pressed Lu2 and the leading components and pressure-induced color changes in nedoped lutetium hydride. Overall, the cited studies demonstrate the ongoing research efforts to understand the properties of lutetium hydrides under high pressure and their potential for superconductivity.